Now we will just go to some calculation. So here you can see a small example circuit. This is the RC low pass filter. So this is the circuit design, right? So we have the resistor here and then the capacitor across the voltage. So here, this is the low pass filter design. I am applying 10 volt and 2 kilohertz input signal at the input, and the output, what output I will get. So you can apply the formula and you can calculate the value. And XC, you don't know what is XC. So XC also, there is a separate formula. XC is equal to 1 divided by omega C or 2 pi FC. You have to calculate the XC and then you can calculate the output voltage. And of course, you can calculate the cutoff frequency also. This is what I wanted you to solve by yourself. But here I give you the solution since I have already uploaded the slides. So you have to first find the FC and then you have to find the value of the output at when the input signal frequency is 2 kilohertz. So then of course you have to find the XC value using this formula, and then the V out, you can apply all the values, then you will get V out value. It's also a very straightforward calculation. So remember here V out is equal to 6.22 volt at 2 kilohertz frequency. I'll show here. So here you can see what we are applying here. We are applying 10 volt. So, okay, this is the cutoff frequency value. So this is the cutoff frequency value, 1.59 kilohertz. So we found FC is equal to 1.59 kilohertz. So with respect to this figure, you can see the green line. So this is the cutoff frequency, and this is the minus 3 dB level. So where this output response is meeting and starting to fall down. We also found a V out at 2 kilohertz. So that is 6.22 volt. So this frequency may be somewhere near the yellow line. So for example, this 6.22 volt, like this, it meets the curve at this point, and then you can just make this one. So this is the cutoff frequency, 1.59 kilohertz, and this is the 2 kilohertz. So that is what we have found in this formula. So at 2 kilohertz, the output value, the magnitude of the output value is 6.22 volt. So remember, what is the low pass filter? Low pass filter, we want to pass only the low frequency signals. We want to stop the high frequency signals. So it means whenever the frequency changes to high, then the output value should go to 0, right? So at the low frequency, we need to have the maximum output. This is the maximum output. This is the 10 volt. Since we are applying 10 volt here. So this is 10 volt. But at the high frequencies, we are increasing the frequencies, the output should go down or it should become 0. But here, I increase the frequency already 2 kilohertz. It's over the cutoff frequency, but the output is not yet 0. It's still falling down slowly. So at 2 kilohertz, I am still getting 6.22 volt at the output. 6.22 volt at the output. So why? Because the falling of the curve is not sharp. It's just going linearly. So that's not really what we want. We want the curve should fall down as soon as possible here. And then when I increase the high frequency, then output should be 0. So that's what I mentioned here. So in this case, filter is not blocking enough. Output is supposed to be 0 for ideal filter, yes. And still there is a slope. Still I am getting some output value at this output terminal. So if we want to make the falling of this slope more sharper, then we need to use higher order filter. So from this example problem, so you can understand why we need to move to the higher order filter. This is the first order filter. Now we must move to the higher order filter in order to make the curve sharper down like this and make the voltage zero as soon as possible for the high frequencies. So it means the slope will decrease more and more. So when you use the higher order filter, the slope will decrease more and more when we increase the order of the filter. So we have a second order, third order, fourth order, and so on. So see the right side top figure Bordeaux plot. Okay, so now you can see this is the ideal response. So we can never get the ideal response. Forget that. For the practical first order filter, it's coming like this, and then the first order filter. This is the first order filter. Where is my pen? So this is the first order filter, the kind of violet line or pink. It's not a pink. Yeah, this color is indicating first order filter response. So the output is not falling down sharply. It's just going linearly like this. So n is equal to 1. It means first order filter. And then I make the second order filter. So what is the frequency response? So now the slope is falling down like this. It's little more sharper than this one. So this is indicating second order filter. So now n value is equal to 2. So this is indicating the order number, second order. And the third order, what is happening? This is little more sharper than this one. So third order filter, it's falling down little more sharper. And then the fourth order filter, and then fifth order filter, sixth order filter. So remember, when you increase the order, so from 1 to 2, 2 to 3, 3 to 4, the curve is falling down more and more sharper. So that is the key point you have to remember. So that is what we want, because the output is becoming 0. For example, in sixth order filter, the output fall down at here when the input frequency, when it becomes 3 Hertz, according to this, it's already falling down. It reached the 0, and then here everything is no more output. So then the low frequency, so the low pass filter is working very good when it becomes higher order filter. So for nth order filter, the slope will roll off 20 dB, 20 times n dB per decade. So remember, I told you in the previous slide, in the frequency response, it's falling down minus 20 dB per decade. This is for the first order filter. So for the second order filter, how it fall down? So it fall down like this. So it means this is second order filter. So second order means the n value is equal to 2. So n times 20 dB. So that is a minus 40 dB per decade. This is for the second order filter. When n value is equal to 3, so n times this standard value, that is the minus 20. So minus 60 dB per decade. So when you increase the order of the filter, this standard value, the first order filter standard value, will multiply it by the n value. So third order means minus 60, fourth order means minus 80 dB, and so on. So that is what I mentioned here, where we are. So here, for nth order filter, then the slope will roll off. It means fall down, minus 20 times n dB per decade. So for example, if you design second order filter, then the roll off will be minus 40 dB per decade. Third order filter means it will be minus 60 dB per decade, and so on. So now please try to understand the theory and some practical filter design. So we thought, okay, we had seen how the filter works and what are the formulas and so on. Here, when we talk about the practical values, you can easily apply this in the frequency response, and you can see here. So even after the cutoff frequency, the output is not 0. So it's still some value because the curve is going down slowly. So we want to make this curve to zero as soon as possible, as fast as possible. For that, we need to increase the order of the filter. That is why we are going to higher order filter.